Good morning, everyone. First of all, thank you to our lecturers and fellow classmates for giving me the opportunity to present today via online. Our presentation is titled The Mathematics Behind Airplane Wings. So, before we begin, let me ask you a simple question. Have you ever looked at an airplane and wonder how something that weighs hundreds of thousands of kilograms can stay in the sky for hours, maybe like 5 to 8 hours or maybe more? It almost seems impossible. But many people think airplanes fly only because of their powerful engines. While engines provide the thrust that moves the airplane forward, they are not the main reason the airplane stays in the air. So, the real secret lies in the design of the airplane wing, and behind that design is a mathematics. Engineers don't simply draw a wing that looks nice. Every curve, angle, and dimension is carefully calculated using mathematical equations. Among the most important equations are linear equations and quadratic equations. So, today I will explain what are linear and quadratic equations are, how their graphs are interpreted, how engineers use them in airplane wing design, and finally, how mathematics and science work together to make airplanes fly safely. By the end or at the end of this presentation, I really hope you will see the mathematics is much more than solving equations in a classroom, but it is something that literally helps airplane flies. Now, let's begin with our first poster. Poster 1 shows that a linear equation in airplane wing. So first, let's look at the linear equation. The linear equation standard form is y is equals to mx plus c, where m is the gradient or slope and c is the y-intercept. A linear equation always produces a straight line graph, but what does the slope actually means? The slope tells us how steep the line is. If the slope is positive, the line rises from left to right. Line left to right. And if it's negative, the line falls. If the slope is 0, the line is completely horizontal like a ruler. Now, you may wonder, how does a straight line equation help with an airplane? Although airplane wings are curved, not every part is curved, like everyone knows, right? Some sections, especially the leading edge, trailing edge, and internal support structures, can be represented using straight lines. Engineers use linear equation to calculate first wing length, alignment, structural angles, and the position of different components. For example, if one support beam needs to connect two points precisely, engineers can use a linear equation to calculate the exact positions. Without this calculation, even a small error could affect the aircraft balance and stability. So, although linear equations look simple, they play a very important role in engineering. Okay, and then we go to the part 2, quadratic equation. Now, let's move to the quadratic equations. The quadratic equation formula is y equals to ax squared plus bx plus c, as you guys are already learned in mathematics, where a controls the shape of the curve, b represents the shift of the graph, but either on the left or maybe it's on the right, and c is the y-intercept. Unlike a linear equation, a quadratic equation produces a parabola, like a curve like a curve. So the curve of graph is extremely important because Airplane wings are not flat. Okay. Instead, they have curved profile known as airfoil. Why is this curve very important in airplanes? It is because the curved surface allows air to move differently above and below of the wing. The difference creates lift, which we will explain later. Engineers use quadratic equation to determine how much the wing should curve, how high the curve should be, where the highest point should be, and how smooth the curve should transition. Even changing the curve by just a few millimeters can affect fuel efficiency, lift, and also safety. That is very crucial for us and also for the pilot and passengers. Therefore, quadratic equations are essential in modern aircraft design, for example, Malaysia Airlines and AirAsia. So, part 3 is a graph of linear and quadratic equation. Now, I would like to compare the graph that's shown here. The first graph is a linear graph. So, our example is y is equals to 2x plus 1. So, I noticed that it forms a straight line because it is similar to linear standard formula or linear standard equation, which is y is equals to mx plus c. So, no matter where we measure it, the slope remains constant. This means the rate of change never changes. Okay? Now, we look at the quadratic graph. The example is y is equals to x squared minus 2x plus 1. Unlike the straight line, the graph forms a U-shaped curve called a parabola. The slope is different at every point. Now, near the vertex, the graph changes direction. So, this changing slope allows engineers to model smooth curves more accurately. Think of drawing with a ruler versus drawing with a flexible strip of plastic. The ruler produces a straight line, which is maybe a straight line like horizontal or maybe a straight line. Okay, the flexible strip produces smooth curve. Airplane wings require both. Straight section provides structural support and curved section improve aerodynamic performance. This is why engineers combine linear and quadratic mathematics in one design. Okay. Now, let's understand the important parts of this graph. First is the x-axis. The x-axis represents the independent variable. Next is the y-axis. The y-axis represents the dependent variable, where both axes meet is called the origin, which has coordinate 0, 0, which is at the x coordinate 0 and y coordinate also 0. For a linear graph, one important feature is the slope. The slope tells us how quickly the graph rises or falls. Like for a quadratic graph, one important feature is the vertex. The vertex is the highest or the lowest point of the curve. Engineers often use the vertex to determine the maximum thickness or the higher curvature of an airplane wing. Another important feature is the intercept. Intercepts are the point where the graph crosses the x or y-axis. This helps engineers determine boundaries and reference points during design. Although these graph components seem basic in mathematics, they become powerful tools when designing real engineering structures. Now, let's compare these two equations, which is linear and quadratic graph. First, their shapes are totally different as we can see. The linear graph is always straight line, horizontal line, and the quadratic graph form a parabola, which consider have a curved shape or U shape. Second, the slope behave differently. A linear graph has a constant slope, where a quadratic graph has a changing slope. Okay. Third, the number of x-intercept is different. A linear graph has at most one x-intercept, and also a quadratic graph can have 0, 1, or 2 x-intercept. Finally, their real-life applications are totally different. Linear equations are used to model straight edges or horizontal edges, while the quadratic equations are used to model curved airfoil. Instead of replacing each other, both equations work together to make sure the airplane flies safely. And then, this combination produces an airplane wing that is both strong and aerodynamically efficient. Now, let's see how these equations are actually used. For example, linear equation helps engineers to calculate wing dimensions, design support beams, determine angles, ensure proper alignment, and improve structural strength. This calculation ensures the planes remain stable during takeoff, flights, and landing. Quadratic equations are even more important for aerodynamics. They help engineers design the airfoil, especially at the wing. The airfoil must create enough lift while reducing drag. Okay, a wing too much curvature creates unnecessary drag. Too little curvature creates an insufficient lift. Engineers therefore use mathematical optimization to find the perfect balance. Modern aircraft, as passenger jets, are designed use thousands of mathematical calculations based on these principles. So, how does an airplane wing works? Finally, let's understand how the wing is actually worked to lift up the airplanes and fly smoothly and safely and stably. So, first, when an airplane moves forward, air flows over both and top-bottom surface of the wings. So, because the top surface is curved, air moves faster across the top of the wing. According to the Bernoulli principle, faster moving air creates a lower pressure. Meanwhile, air below the wing moves more slowly, creating a higher pressure. And also, according to the Bernoulli principle, lower moving air creates a higher pressure. Okay. This pressure difference pushes the wing upward. That upward force is called lift. Lift is the force that keeps the airplane in the air. Without the without the correct curve, the pressure difference would not be large enough, and also the airplane would struggle to fly efficiently, although the safety will be disrupted. This shows that mathematics directly influence physics. The equations determines the wing shape, and the wing shape determines the airflow. The airflow creates lift. So, mathematics is actually the foundation of the flight. Okay. To conclude that, today we have learned that mathematics is much more than solving problems in textbook or examinations. Linear equations help engineers design straight structural components. Quadratic equations help engineers create the curved airfoil that produce lift. By analyzing graph, slope, vertical, intercept, engineers can design airplane wings that are safe, efficient, and fuel-saving. When combined with scientific concepts such as Bernoulli principles, these mathematical models makes modern air travel possible. So, every time we board an airplane, for example, like say Malaysia Airlines or AirAsia or more, we are actually experiencing the practical application of mathematics and science that work together. So, next time when we see an airplane flying across the sky, remember that behind every successful flight are countless mathematical calculations that made by engineers. As our poster said, math gives wings to imaginations and flight. Thank you very much for your attention.